In this video, we will explore the concept of simultaneity. In our everyday life, simultaneity isn't an important concept, as we live in a reality in which the speeds at which we move around are very small, compared to the speed of light. However, if we could observe events where the speeds of motion were a fraction of the speed of light, then simultaneity changes dramatically. Actually, according to special relativity, simultaneity is relative to the observer. Let's think of the following experiment. Suppose that you put two light sources, A and B, separated by a distance d. The sources are identical and are connected, in such a way, that you can turn them on and off with a single switch. A timer will keep track of the events on the experiment. Then, you ask your friend Alice to stand right at half of the distance between the light sources. Also, you ask your friend Vivian to run from the source B to the source A as fast as she can. At the precise instant when Vivian reaches the position of Alice, you generate a flash of light. It's natural to ask, when will Alice and Vivian see the light flashes? In our own experience, this question doesn't make sense, as we know that the flash of light will be seen by Alice and Vivian at the same time. This is because, as we said before, in our lives, we move at speeds much lower than the speed of light, right? But now, let's suppose that Vivian can run as fast as a fraction of the speed of light. What will they see in this case? In this situation, we will use a tool known as spacetime diagrams, where we can show displacement and time in a graphic way. In the spacetime diagram, the vertical axis is the time and the horizontal one is one of the spatial coordinates. For the case we are analyzing, there is only one, the horizontal direction. Now, think of the positions of the source A and B. They don't change position along the experiment. Then can be represented as vertical lines in the spacetime diagram. The same happens for position of Alice. On the other hand, the flash of light from the source A should follow an oblique path in the diagram as it moves to the right. The same happens for the flash from the source B, but in the opposite direction. For the case of Vivian, as she's moving to the left, she also will present an oblique path to the left. Note how for Alice, the flashes of light arrive to her position at the same time. In contrast, Vivian sees the light from the source A, and later, the flash of source B, because she is moving away from B. This is a clear example of the relativity of the simultaneity. We can study three interesting cases, using the spacetime diagrams. First, when the speed of Vivian is much smaller than c as most of the cases of our everyday life. Her displacement, with respect to any displacement of the flashes of light, should be negligible. Then, she should experience the same as Alice. Note that in the diagram, the speed of Vivian is exaggerated to show the make our point. In the second case, if the speed of Vivian is an important fraction of the speed of light, then she will have an experience completely different as Alice. Actually, she will observe that the flash of light coming from A and then the flash coming from B. The difference in time between the two flashes will depend on her speed. Finally, in the third case, Vivian moves at the speed of light. In that case, she will see the flash of light from A much earlier than in the previous cases. But, more importantly, she will not see the flash from B, as that light will not reach her. Do you remember the Einstein's postulates? Well, this last result is precisely a consequence of those postulates. Unfortunately, as we will study soon, a body with mass different to zero can't move at the speed of light. Then, the experiments of this video only have a learning purpose. Unless, in the future, some of you find the way to go around this impossibility. Stay tuned.